Okay, starting at 4.3, binomial distribution. Okay, the next two are pretty important lessons. You need to figure out you need to know each one. They're very similar, but you have to recognize which is binomial, which is hypergeometric in order to identify the formula you need to use. Okay, so binomial is independent trials. The key there, independent trials. Okay, let me rewind. So 4.1 was binomial distributions, probability distribution, which is make the chart. Then we looked at uniform distribution, that's where all outcomes are the same. Okay, now we're going binomial distribution, so we're now on multiple trials. Uniform was one trial, binomial is multiple trials, and tomorrow, which is hypergeometric, is also multiple trials. Okay, so these ones are going to be independent. Okay, so independent trials, that's where one trial does not affect the next. Okay, we're going to consider them either success or failure. Okay, and it doesn't mean failure as if they're failing. It's usually what we're looking at versus what we're not looking at. So what we're looking at, what we're not looking at, and this has replacements. Okay, the random variable equals the number of successes in a given number of trials. Okay, so the formula here is NCX, not NCR, NCX, P to the power X, and then Q n minus X. Okay, that's my markers. So N is the total trials. Okay, then we have X, which is our number of successful trials. Number of successful trials. Okay, P is the probability of success. Probability of success. And Q is the probability of failure, but I don't like it. The word failure. More of not success. Okay, so what we're not looking at. Okay, then we have expectation once again. So the expectation is N times P. Okay, so uniform it was a little bit different. We had the EX, we had the sigma. Okay, but here for EX is N times P. So number of trials times the probability of success. Okay, I'm going to scroll down. Okay, a card is repeatedly cut from a deck and replaced each time. What is the probability that in 10 trials an ace is cut? Okay, so we have multiple trials. Okay, so we cut the deck and then replace it. So that means it's binomial, so it's independent trials. Because if we take the card out and we put it back, we still have 52 cards each time. Okay, so what's the chances that we get an ace? Well, how many trials are there? We have 10 trials, so 10p, and then we want, how many do we want? We want an ace once. Okay, so we want ace once. We want one ace. Okay, now the probability of success. So what's the probability? In this case, our success is actually getting an ace. So what is the chances of getting an ace? Well, it's 4 to 52. 4 to 52 chance to get an ace, or you could have 1 out of 13. Okay, and then you see this is the power of X, so it's 1. And then the non-success, or the failure, is not getting an ace, which would be 48 over 52, and 10 minus 1 is 9. So we just want one trial, one ace from this probability, and this one, 9 other cards, 9 other trials to get the rest of the cards. So if you plug that in, I got here 0.37 or 37%. So if you were to cut a card 10 times from a deck of cards, 37% chance there will be one ace. Okay, next one. What is an ace is cut 3 times? So now 10 trials, we want to, sorry, I don't know why I put P here. My apologies. C, 10 choose 1. So 10 choose 3 now, because we want, out of our 10 trials, we want 3 aces. So I'm just going to redo the reduced form, so 1 over 13 to the power of 3, and the remainder is 12 out of 13 to the power of 7. Okay, you expect the probability to decrease. To get an ace 3 times is unlikely. So when you plug this in, you get the answer of 0.03, which is 3% chance. Okay, Mr. McKenzie has 4 children. I do not have 4 children, but just for the example, consider a probability distribution for the number of boys in the family. Okay, so first identify the discrete random variable. So discrete random variable is what we're looking at, and that would be the number of boys out of the 4. Okay, B, calculate the probability distribution. Okay, so it gets a little tedious. So probability distribution, remember this represents a chart. So we want to go through all the possible outcomes and its probability. So we have the outcomes and the probability, P at X. So our outcomes, out of 4 children, how many boys can I have? Well, I could have 0 boys, all the way up to 4 boys. Let me space this out a bit more. So I could have 0 boys all the way up to 4 boys. So you see having a children, on the last test, a lot of you guys put this as an example. If you have a child, if you have one child, it does not affect the gender of the next the sex of the next child. Okay, so each child is considered an independent event or a trial here. Okay, so we have multiple trials. And since we want to look at all the different ones, we're using our binomial formula. So, number of trials in this case is 4. Each child is a trial. And first we want 0. Okay, so what is the probability of having a male every time? Well, it's 50%. You can put 0.5 or you could put a half, it doesn't matter. And so in this case, it's success. And the probability of non-success. And like this, it just means what you're looking at versus what you're not looking at. So we're looking at males here, we're not looking at females. So then we have 0 over 4. If you use a decimal or a fraction, it's up to you because we're doing probability, so you could use any form. We're going to continue that. 4 choose 1. So 0.5 to the power of 1, 0.5 to the power of 3. 4 choose 2. Remember the formula says this is x and then this is n minus x. So then 4 choose 3. By the way, this is the same formula that we used for binomial theorem, which is for Pascal's triangle. And lastly, 4 choose 4, sorry, expanding. Okay, so that's the whole chart, and our answers, which I have written here, are 0.0625, so 6% chance to have 0 boys out of the 4, 0.25, so a 25% chance you have 1 out of 4, 37.5% chance that it'd be 2 boys, 25% chance that it'd be 3 boys, and 0.0625 or 6.25% chance that it'd be all males. Okay, our very last question now. Oh, calculate the expectation, sorry. So expectation, so E at X. In this case, since it's binomial, it's N times P. So the number of trials in this case is 4 times the probability of 5. So 4 times a half, which is 2. So how many males should you expect? And a litter, of 4 children, you should expect 2. Last one. Okay, the failure rate is 10% in the initial production of a new calculator chip. A quality control inspector selects 20 chips for testing. What is the probability that more than 2 of them are defective? More than 2. So that means 3, 4, 5, all the way up to 20. So this is one of those questions where we have the at least. So this is like at least 3, or it says more than 2. So you have 2 defective chips, 3, 4, 5, all the way to 10. So we could calculate each defective one from 3 all the way to 20, but that would take a lot of work. So instead, what we usually do is we find out the whole, in this case 100%. So we're going to do 1 subtract 0 defective chips, 1 defective chip, and 2 defective chips. So we're going to do, 1, we're 100%, subtract 0, subtract 1, subtract 2. These are defective chips, defective chips, defective chips. So 1 minus, now we'll say the probability of having 0. Okay, so since the question is, well, how do you know if it is independent trials here? So it's just a percentage. Okay, so every trial you still have every chip is 10% chance that it will be defective. So if one's not, it's not going to affect the defective rate of the next one. It's just 10% for each one. Okay, so what is the probability that more than 2 are defective? So again, 1 minus the rest. So the trials are the 20, so we have 20 chips, and we want to have 0 defective ones. Then the chances, so this would, the success in this case, because we're looking at defective chips, we're looking at success as the defect, okay, because it doesn't make sense. So what we're looking at are the defective ones. So what's the probability of defect? It's 0.1, okay, to power 0, and then that would be 0.9 to power 20. So kind of doesn't make sense. You're like, oh, what's the probability of success for a defective chip? Well, how could that be successful, something that's defective? So what I like to say is what we're looking at versus what we're not looking at. So 10% chance of defectiveness versus 90% not. Okay? Then we're gonna have, you could do add these all or subtract them. I'll just do subtract. Subtract now 1. So 20 choose 1, 0.1 to power 1, 0.9 to power 19. Subtract, last one, which is 20 choose 2, 0.1 to power 2, and 0.9 to power of 18. I do not have an answer here. That kind of stinks. .1216. Something's wrong here. Let me do this one again. Yeah, this one is wrong. I'm just going to try this one more time. 0.9 to power of 20. Yes. Okay, now we subtract them all. 1 minus 0.1216 minus 0.3234 or 32% chance. So if we had a 20 chips, the chances that there were two are more than two, so more than two would be three or more chips would be defective would be 32% chance. Okay, and what is the expectation? So that's the expectation is the number of trials, which is 20 chips, and the probability of success, or in this case defectiveness, is 0.1. So we should expect 10% of 20 is 2. So we should expect 2 out of the 20. Okay, homework is here at the bottom, page 167, 1, 2, 3, 5, 6, 7, 8, 9, A, B, and 10. It is a challenging section, this one and the next. Please, please, please make sure you get the homework done. If you do not get it complete, you're going to be in trouble for the test.